Another important feature of MATLAB programming is functions. Functions stem from a more traditional way of programming, in which specific sets of calculations are defined using a function file. This file type, unlike a script, is not free of restrictions, and requires a certain format in order to be used or called later. Another word for function is subroutine, which stems from the fact that functions essentially serve scripts within the present directory by doing predetermined sets of calculations on the input or arguments, and returning the output of these calculations. Functions are not always necessary, but when you do need them, you will almost always need to write a main driver script to call the function. Let's start off with an example. We will write a function to calculate the eigenvalues of a given 2x2 matrix. To do this, we must first create a driver script, which is traditionally named main. Within the present directory, we can create this script and name it main. For this example, we will also be making a function file, which we still name eigen. Note that the functions should be named according to their purposes. In the newer versions of MATLAB, the files are separated according to their types as well. For example, eigen is under MATLAB function and main is under script. Now we will write the eigenvalue solver. You will learn how to solve for eigenvalues later in linear algebra, but for our purposes, just know that the eigenvalues of a 2x2 matrix are the solutions to the following quadratic equation: lambda squared minus lambda times the trace of A plus the determinant of A equals 0, where trace of A is the sum of its diagonal and A is the matrix. We will start off with the function definition. Double-click on eigen.m. Notice that there is pre-generated content. Essentially, what you need to define for all functions is what the function will take along with what the function will return. The input args must be replaced with our input matrix, which we will call A for clarity and consistency. After this, we know that we will return two values, which we'll store in a variable which we will arbitrarily name output, also for clarity's sake. In the comment area, which is denoted by green text, we will describe the function's purpose for the sake of our readers. The following phrase will suffice: solves for the eigenvalues of a 2x2 matrix. Now we are ready to define our calculations, which will take place between the function and end keywords. We can think of A as an external input that is given to us within the context of this function, and therefore it is predefined. We also assume that A is a 2x2 matrix, and therefore has 2 rows and 2 columns. We will define 4 local variables A, B, C, and D, where A is the top left, B is the top right, C is the bottom left, and D is the bottom right, with the following lines: A equals A, 1, 1, B equals A, 1, 2, C equals A, 2, 1, and D equals A, 2, 2. After this, we will calculate the trace of A, which is the sum of the diagonal, or A plus D. Trace, or TR, equals A plus D. We also need the determinant of A, which is the difference between the main diagonal and the anti-diagonal. Determ equals A times D minus B times C. Note that we have named the variables according to what they calculate, for clarity's sake once again. Now we will allocate the memory for the output. While this is not a necessary step, it will provide insight into pre-allocation of memory for variables. One standard way of allocation is to simply fill it with zeros, and since we know our output will be a 1x2 matrix, 1 row by 2 columns, we type the following: output equals zeros, 1, 2. Now all we have to do is solve for lambda. Using the same technique from lesson 2, we finish the computation with the quadratic formula: A equals 1, B equals trace, C equals determ, D equals square root sqrt, B to the power of 2 minus 4 times A times C. And finally, output 1, 1 equals minus B plus D divided by 2 times A, and output 2, 1 comma 2 equals minus b minus d divided by 2 times a. Note that to save memory, we have overwritten a, b, and c. Note also that we directly set values in output via indexing. Finally, know that all variables created within a function are purely local, meaning they are destroyed as soon as the function ends, at the end of their function call. We have finished our function definition, and all that remains is to call the function. We cannot do this by itself, so we need to open main, the script, and we will randomly create a 4x4 matrix with a equals magic 4. Note that it is perfectly okay to use variable a even if we use the function call, because the function has its own scope. In other words, functions are oblivious to the script's variables and vice versa. While it is possible to share variables between scripts and functions, this is a more advanced topic and is rarely used. We know A is a 4x4 matrix and its 4 quadrants contain 2x2 matrices. We will solve for each set of eigenvalues with the following lines. E1 equals eigen A 1 colon 2 1 colon 2. E2 equals eigen A 1 colon 2 3 colon 4. E3 equals eigen A 3 colon 4 1 colon 2. And E4 equals eigen A 3 colon 4 3 colon 4. Note that each submatrix can be directly indexed and passed to the eigenfunction. Now the eigenvalues for all 4 submatrices are stored in E1 through E4, and we can condense the results into a 2x4 matrix with results equals E1, E2, E3, E4. Now hit F5 and run the script. And look at results. In closing, functions have many opportunities for use, and in this case, it was used to condense otherwise repetitive code. Subroutines are a highly effective and easily readable way of generalizing and automating repetitive calculations and splitting them into external files.